Hello everyone, my name is Nat Nikolov. I'm a physical scientist with the U.S. Forest Service specializing in applied fire weather research and application development using climatological data to assist the fire management in the United States. I list my affiliation here as an independent researcher because this study was conducted outside of my government duty hours. My co-author and free spirit, on the other hand, Dr. Carl Zeller, is a retired Forest Service physical scientist. This poster presentation is entitled Role of Albedo in Planetary Climates, New Insights from a Semi-empirical Global Surface Temperature Model. It discusses an extension to the 2017 Nikolov-Zeller Planetary Temperature Model that describes the effect of cloud albedo variations on the global annual surface temperature of rocky planets and moons, including Earth. I'd like to begin with a preface. This poster was presented at the American Meteorological Society 101st Annual Meeting on January 12, 2021, and complements an oral talk entitled Implications of a Semi-empirical Planetary Temperature Model for a New Understanding of Earth's Paleoclimate History and Polar Amplification, given at the same forum and now available on YouTube at this address. For best understanding of this new climate concept, we strongly recommend watching the above oral talk in addition to this presentation. The oral talk discusses drivers of Earth's long-term baseline planetary temperatures over thousands to millions of years, while this presentation addresses causes of surface temperature variations operating on timescales of decades to centuries. Also, viewing both video presentations more than once is highly advisable to fully grasp this new concept about climate change. Available surface and satellite global temperature records indicate that the Earth has warmed about 1.1 degrees Celsius or Kelvin since 1850, with most of that warming, 0.7 degrees Celsius, occurring over the past 42 years. This raises the question, what has caused our planet to warm? According to the prevailing greenhouse theory of climate change, the Earth has warmed primarily in response to rising atmospheric concentrations of radiatively active trace gases emitted by human industrial activity, with carbon dioxide or CO2 delivering the greatest infrared radiative forcing. Indeed, the increase of atmospheric CO2 since 1850, and particularly since 1979, is well correlated with the rise of global surface temperature. Of course, a correlation does not imply causation, but causation cannot exist without a high correlation. However, temperature reconstructions for the past 2 millennia, based on various proxies, reveal that the observed warming of the past 170 years was likely not unique. According to some reconstructions, global temperature has fluctuated plus minus 1 degree Kelvin around a long-term semi-stable baseline since the beginning of the Common Era, as shown by the plot on the left. When such long-term records are considered, atmospheric CO2 shows no longer a strong correlation with global temperature as depicted by the plot on the right. This fact broadens our initial question to what caused the observed decadal fluctuations of global temperature around a stable baseline for the past 1,000 to 2,000 years? To answer it, we turn our attention to the satellite era, a period from 1979 to the present, where planet-wide gridded observations of climate variables became available. Our premise is that drivers of climate warming in the past 40 years must have also operated during the past 2,000 years. A plethora of studies published over the past 15 years revealed that both regional and global scale warmings have been associated with observed decreases of Earth's cloud albedo and the subsequent increases of surface solar radiation, a phenomenon often referred to as solar brightening. Reduction of cloud cover has also been found to be the driver of ice sheet melting in Greenland. Researchers have been wondering for a decade now whether a CO2-induced warming has reduced the low-level clouds as suggested by climate models, or a cloud cover reduction driven by an external cosmic forcing not simulated by models has warmed the Earth. Regardless of differences in viewpoints, it is indisputable that the observed decrease of cloud cover and albedo, mostly due to a reduction of low-level clouds, has led to an increased absorption of solar radiation by the planet's surface. Hence, understanding the effect of cloud albedo on Earth's surface temperature is crucial. However, the issue is more complicated than meets the eye because the relationship between global surface temperature and the planet albedo is not straightforward. Here is why. According to the Stefan-Boltzmann radiation law, the equilibrium temperature of a material object is proportional to the fourth root of the radiation absorbed by the object. As shown by the equation in the upper left corner, the spatially averaged shortwave flux absorbed by a planetary body, S sub A, is a function of the top of the atmosphere solar irradiance, S, and planet's albedo alpha, defined as the fraction of incoming solar radiation reflected back to space. Yet across the solar system, the observed global surface temperatures of planets and moons appear to have no relationship to absorb solar radiation by such bodies as illustrated on this scatter plot. Note that the 6 planetary bodies shown here span a broad range of albedos, that is from 0.36 for the Moon to 0.9 for Venus. The higher the albedo, the lesser the amount of absorbed solar radiation by a planet. One can see that Venus, although being closest to the Sun, absorbs less shortwave radiation than Mars, Earth, and the Moon because of its high cloud albedo. However, Venus has an average surface temperature of 737 Kelvin, which is higher than the temperature of any other planetary body in the solar system. Earth absorbs about 54 watts per square meter less shortwave radiation than the Moon because of its reflective cloud cover. Yet Earth is some 90 degrees warmer than the Moon. Hence, observations clearly indicate that the surface temperatures of rocky planets and moons are not meaningfully related to planetary albedos and the amounts of absorbed solar radiation. Is this a violation of the Stefan-Boltzmann law? No, it is not. There are 2 reasons for the observed lack of a relationship between these variables. The first reason is mathematical in nature and arises from nonlinear interactions between temperature and radiation on the surface of a spherical planet. Since temperature is a power function of absorbed radiation according to the Stefan-Boltzmann law, and the intensity of solar radiation varies as a cosine of latitude, meaning nonlinearly, across the surface of a sphere, the spatially averaged absorbed solar flux simply cannot predict the global average surface temperature of a planet. This is explained by Hildreth's inequality between integrals discussed in this 2014 paper, which I strongly recommend as background reading. In other words, a spherically averaged solar flux is mathematically incompatible with a spherically averaged surface temperature. This makes the canonical 33-degree estimate of the atmospheric greenhouse effect based on such average absorbed solar flux numerically and physically incorrect. The actual thermal effect of Earth's atmosphere, when computed correctly, turns out to be about 90 degrees Kelvin. This fact alone has serious implications for the greenhouse theory, since a 90-degree thermal effect cannot be explained by the observed 158 watts per square meter absorption of outgoing long-wave infrared radiation by Earth's atmosphere. The second reason comes from a discovery made by Nicola von Zeller about the physical nature of the atmospheric thermal effect discussed in this 2017 paper. By applying dimensional analysis to vetted NASA planetary data, Nicola von Zeller found that the atmospheric thermal effect, or ATE, currently known as the greenhouse effect, is a form of adiabatic heating, also known as compression heating, caused by total air pressure that is independent of atmospheric composition. The long-term baseline temperatures of rocky planets and moons turn out to be a smooth and continuous function of only 2 factors: top of the atmosphere solar irradiance and mean surface atmospheric pressure, despite a broad range of observed albedos. The Nikolov-Zeller model requires no knowledge of the infrared radiative transfer in the atmosphere to accurately predict global planetary surface temperatures, which implies that atmospheric infrared radiation is a consequence of the atmospheric thermal effect rather than a driver of climate, as currently believed. These findings have several major implications for our understanding of the climate system, one of which is that the bulk or baseline albedo corresponding to a planet's baseline surface temperature is a byproduct of the climate system rather than an external controller of climate. Stated otherwise, the baseline albedo of a planetary body is an intrinsic property of the atmospheric thermal effect. This does not mean that external forcing such as solar wind or galactic cosmic rays cannot influence the cloud albedo, and that albedo perturbations generated by such forcing cannot impact planet surface temperatures. They certainly can. However, the presence of a baseline albedo set by planet's long-term surface temperature and atmospheric pressure implies that the forced albedo perturbations are likely to be small compared to the baseline albedo due to a stabilizing effect of negative feedbacks operating within the system. This figure depicts the single most important result from the 2017 Nicola von Zeller study. The relative atmospheric thermal effect, defined as a ratio of a planet's observed long-term global surface temperature under an atmosphere T sub S to the planet's hypothetical surface temperature without an atmosphere T sub Na, is completely defined by the mean atmospheric pressure at the surface and does not depend on planetary albedos, denoted here by alpha, ranging from 0.136 to 0.9 across the 6 bodies. This is the equation derived by Nicola von Zeller 2017 based on NASA data that describes the global baseline surface temperature of rocky planets and moons as a product of two terms. A, the no atmosphere or airless global temperature T sub Na, highlighted in yellow, and B, a dimensionless atmospheric thermal enhancement E sub A, quantifying the relative effect of pressure on temperature, highlighted in blue. The second term describes the red curve we saw on the previous slide. Note that this equation does not contain a cloud albedo variable, yet it predicts quite accurately the baseline temperatures of 6 planetary bodies spanning a broad range of physical environments in the solar system. The ability to accurately model long-term global surface temperatures of planets and moons without explicitly accounting for planetary albedos indicates that the total albedo is a byproduct of the climate system rather than a determinant of the global surface temperature, which is counterintuitive. This is a key new finding about the role of albedo in climate. This slide illustrates the concept of a baseline global surface temperature on Earth using two recent reconstructions based on various proxies. The baseline temperature is the long-term semi-stable value depicted with a dashed regression line on each plot. Although these reconstructions employed different methods that yielded vastly disparate patterns of decadal variability, the 1,000-year baseline temperatures are remarkably similar between the two time series and only differ by about a quarter of a degree. This data suggests that Earth's baseline global temperature has been around 286.4 degree Kelvin or 13.2 degree Celsius for the past 1,000 to 2,000 years. The question is, what caused the global surface temperature to fluctuate around a semi-stable baseline value on decadal to centennial timescales? We address this by formulating a testable hypothesis based on our finding about the adiabatic nature of the atmospheric thermal effect, as well as published satellite observations of cloud albedo dynamics for the past 40 years. Our hypothesis is as follows. Observed variations of Earth's global surface temperature on a decadal timescale are caused by changes of global cloud cover and albedo rather than greenhouse gas concentrations. To test this hypothesis, we propose to use a generic model derived from first principles that mathematically links deviations of the planetary albedo from a baseline value to changes in planet's global surface temperature. If cloud albedo variations have been driving the warming in recent decades, then our model should be able to reproduce observed trends of reflected solar radiation by Earth without consideration of non-condensing greenhouse gases. What would constitute a verification of this hypothesis? If our independently derived albedo temperature model correctly reproduces Earth's reflected shortwave radiation measured by the Clouds and Earth's Radiant Energy System, or CIRRUS, between 2001 and 2019, then the above hypothesis is verified. CIRRUS is an advanced satellite-carried radiometer launched in year 2000. Modeling the response of global temperature to albedo deviations from a baseline value. This slide illustrates the derivation of our albedo temperature model. We begin with the Nikolov-Zeller formula, which completely describes the long-term global surface temperature of rocky planets and moons throughout the solar system. Although this formula does not contain an explicit albedo variable, it can be applied along with the chain rule of calculus and spherical geometry to yield an analytical expression relating the deviation of planetary albedo delta alpha from a baseline to a change of global temperature delta T from a long-term mean. Equation 1 is a simplified form of the Nikolov-Zeller formula valid for planetary bodies with tangible atmospheres. It describes the baseline surface temperature of a planet T sub SB as a function of top of the atmosphere solar irradiance and pressure-dependent atmospheric thermal enhancement E sub E. First, we define the functional dependence of delta T on changes in absorbed solar radiation delta S. Equation 2 shows the total derivative of a planet's baseline temperature with respect to absorbed solar radiation S sub A as a function of 4 partial derivatives in accordance with the chain rule of calculus. Equations 3, 4, and 5 quantify the component partial derivatives listed in equation 2. Equation 4 estimates the average absorbed solar radiation by a planetary body S sub A using spherical geometry. The parameter alpha sub B in equations 4 through 8 denotes the baseline planetary albedo, which is an emerging property of the climate system as discussed earlier. Equation 6 is the final expression for the total derivative of the baseline global temperature with respect to absorbed solar radiation S sub A, obtained upon substituting in equation 2b the partial derivatives defined earlier. Equation 7a integrates equation 6, while equation 7b shows the final result of that integration, which quantifies delta T as a function of delta S. This expression implies that the global temperature sensitivity to absorbed shortwave radiation is proportional to the absolute temperature and increases logarithmically with the baseline albedo alpha sub B. Upon replacing delta S in equation 7b with its equivalent in terms of albedo anomaly delta alpha, we arrive at equation 8, which describes the change of global surface temperature delta T caused by a change in planetary albedo delta alpha. Note that equation 8 only produces a non-zero value for delta T when delta alpha differs from 0. Thus, according to this objectively derived model, the global surface temperature of a planet does not deviate from a baseline value T sub SB set by solar irradiance and total pressure if the planetary albedo does not depart from its intrinsic long-term value alpha sub B. Equation 9 describes the planet's mean annual global average temperature as a summation of the baseline temperature T sub SB and an albedo-controlled anomaly delta T. It should be noted that the derivation of the albedo temperature model, which is equation 8, using partial derivatives, would not have been possible without the integral equation 1, which completely describes the absolute global surface temperatures of planetary bodies across a broad range of conditions. Graphical illustration of the new albedo temperature model. It is important to point out that our model predicts a unique temperature sensitivity for every rocky planet and moon in the solar system. That's because the temperature anomaly delta T in response to a unit albedo change is proportional to planet's baseline global surface temperature and increases logarithmically with the baseline albedo. The plot on the left illustrates the response of delta T to delta alpha for four planetary bodies with tangible atmospheres: Venus, Earth, Mars, and Titan. Note that although delta T is a logarithmic function of delta alpha, the response curves look as straight lines due to the narrow range of albedo variations considered. The steeper the response curve, the higher the sensitivity of the planet's global temperature to an albedo change. Venus has 19 times the climate sensitivity of Earth because of its hot surface, 737 Kelvin, and a high baseline albedo of 0.9. Earth's climate sensitivity is about minus 1 degree Kelvin per 1% change in albedo. Mars and Titan have lower climate sensitivities than Earth, primarily due to being further away from the Sun and having cooler surfaces as a result. A high surface temperature sensitivity to albedo variation signifies the presence of strong negative feedbacks in the climate system that limit the magnitude of possible albedo anomalies. Hence, Venus is expected to have a much more stable cloud albedo than Earth or Mars. It is these negative feedbacks, along with the intrinsic nature of the baseline albedo as an emerging property of the climate system controlled by total pressure and solar irradiance, that is responsible for the observed relative stability of planetary albedos across the solar system. This is an extended version of the Nichols-Zeller planetary temperature formula incorporating the above albedo effects. A planet's global annual average surface temperature is now a product of three terms. A, the no-atmosphere temperature T sub Na, marked in red. B, the pressure-induced relative atmospheric thermal enhancement E sub A, marked in blue. And C, the effect of albedo anomaly on global temperature, marked in yellow. Note that if delta alpha equals 0, the albedo term reduces to 1, and the global annual temperature T sub S becomes equal to the planet's baseline temperature solely determined by solar irradiance and mean surface pressure. If delta alpha is greater than 0, then the global temperature falls below the baseline value. Conversely, if delta alpha is smaller than 0 or negative, the global temperature rises above the baseline. Thus, varying the albedo anomaly causes the global temperature to fluctuate around a long-term stable mean. Stated more conceptually, the atmospheric pressure and distance from the Sun determine the bulk kinetic energy of a planet's climate system, which sets a global temperature baseline while giving at the same time a rise to an albedo as an emergent intrinsic property of the system. External cosmic forcing can perturb this intrinsic albedo to some extent, causing limited transient departures of global surface temperature from the baseline. However, only changes made to the total pressure of the amount of solar energy reaching the top of the atmosphere can alter the global baseline temperature and the intrinsic albedo. While the baseline temperature of a planet is predictable using a top-down approach like ours, the baseline intrinsic albedo is not, since it is an emergent system property. This is an important conclusion from our analysis. This equation can be inverted and solved for the albedo anomaly delta alpha as a function of global temperature, allowing one to predict changes of Earth's reflected solar radiation from observed global surface temperatures. Such predictions can then be compared to independent satellite-based measurements of Earth's reflected shortwave flux to test the hypothesis that the observed warming in recent decades was caused by a decreasing cloud albedo rather than increasing atmospheric greenhouse gases. We performed such a model inversion. Evidence for cloud albedo control of Earth's climate from annual data. This slide shows results from the application of the inverted NZ model to estimating Earth's average annual reflected solar fluxes using two global near-surface temperature records as input. A, the University of Alabama at Huntsville Lower Troposphere Satellite Record version 6, based on remote sensing by microwave sounding units, and B, the Hadley Center Climate Research Unit Temperature Record version 4, based on surface thermometer measurements. The NZ model predictions of reflected solar radiation, colored in blue, are compared to independent annual global reflected shortwave fluxes measured by the clouds in Earth's Radiant Energy System, or CIRES, colored in red. CIRES, which has been operational since year 2000, is the most advanced satellite-based radiometer currently flying in space that measures emitted and reflected radiative energy from the Earth's surface and the atmosphere. As one can see, model predictions fall on top of measured fluxes and are within 33% of the CIRES calibration uncertainty, suggesting an excellent model performance. Also, downward trends of reflected solar fluxes are not statistically different between modeled and measured time series. The overall negative trend of the reflected solar energy implies that Earth's cloud albedo has been decreasing for the past 20 years. The close agreement between modeled and observed reflected shortwave fluxes indicates that the warming of the past 2 decades has been caused by a declining cloud albedo rather than increasing atmospheric concentrations of greenhouse gases. Evidence for cloud albedo control of Earth's climate from monthly data. This slide depicts a similar model data comparison as the previous one, but using smoothed monthly data. Again, model projections of albedo variations inferred from near-surface temperature records employing different measuring methods match remarkably well seasonal variations and multi-year trends of observed reflected solar radiation by CIRES. Our analysis revealed that the best model data match is achieved when the smoothed CIRES time series is shifted 7 months forwards. This implies that the global surface temperature responds to changes in cloud albedo with a lag of 7 months. The presence of such a lag further strengthens the conclusion that observed interannual variations in decadal trends of global surface temperature are controlled by changes in Earth's cloud albedo rather than human carbon emissions. Published research has suggested that since magnetic activity has likely been forcing cloud albedo changes either directly through the solar wind or indirectly by modulating the flux of galactic cosmic rays, which in turn affects the production rate of cloud condensation nuclei in the lower troposphere. However, the exact mechanisms of cloud control are still not sufficiently well understood to be included as mathematical algorithms in climate models. Hence, more research is needed on this important topic. If changes of cloud albedo drove global surface warming during the past 2 decades, we can safely assume that this mechanism has also operated throughout the 20th century and beyond. As pointed out earlier in the presentation, a number of studies published since 2004 found that cloud cover has decreased and surface solar radiation has increased since 1979, both globally and regionally. Thus, we can apply our albedo temperature model to simulate or reconstruct the likely dynamics of Earth's albedo back in time using observed long-term global temperature records as input. Why did Earth start warming 160 years ago? Figure 1 on this slide shows the observed global warming since year 1700 according to a proxy-based reconstruction by Luedecke and Weiss, 2017, and satellite records from 1979 to the present. Figure 2 depicts the modeled dynamics of Earth's albedo inferred from the temperature record that could explain this warming. A 1.1% reduction of cloud albedo from 0.3 to 0.289 would have been sufficient to account for the observed 1.1 degree warming since 1860, according to our model. Figure 3 portrays the increase of absorbed solar radiation in response to the model decrease of cloud albedo. We suggest that the warming of the past 160 years was likely caused by an additional 3.7 watts per square meter absorption of solar energy by the planet. In other words, we surmise that Earth has escaped from the Little Ice Age thanks to a reduction of global cloud cover induced by the sun. Note that our model, which has been verified against serious observations, estimates Earth's global temperature sensitivity to absorbed solar radiation to be about 0.3 Kelvin per watts per square meter of absorbed radiation. For comparison, climate models predict a temperature sensitivity to CO2 in the order of 0.8 Kelvin per watts per square meter. However, as pointed out earlier, our analysis of NASA data showed that Earth's climate is insensitive to trace gases such as CO2 due to their minute partial pressures in the atmosphere. This slide depicts model dynamics of Earth's albedo and absorbed solar radiation for the past 2020 years, estimated from proxy-based reconstructions and instrumental records of global surface temperature variations shown on Figure 1. Note that the modeled albedo shown in Figure 2 varies about plus minus 1% around a baseline value of 0.3, while the modeled absorbed solar radiation shown in Figure 3 fluctuates between 235 and 242 watts per square meter. Modeled albedos during the satellite era, 1979 to the present, closely match NASA observations made by the CIRRUS and the ERBE instruments. ERBE stands for the Earth Radiation Budget Experiment, a NASA-funded project that was executed in the 80s. This model simulation of Earth's albedo changes from the start of the last millennium to the present illustrates our new concept that decadal to centennial variations of global temperature are driven by externally forced changes in cloud albedo. If a decrease of cloud albedo was responsible for the observed warming over the past 160 years, could we expect this mechanism to continue operating in the future as well? We think the answer is yes. What will determine climate change over the next 100 to 200 years? Our hypothesis is that sun-induced modulations of cloud albedo will determine the direction and magnitude of climate change over the next 100 to 200 years. In the context of our global temperature model, this is quantified by the variable delta alpha. Unfortunately, no current models can predict changes of Earth's cloud albedo decades into the future. Hence, this is where research funding should be focused if we are to develop robust capabilities to forecast Earth's climate. Current CO2-driven global circulation models cannot correctly predict future climates because the Earth system is not governed by non-condensing trace gases as assumed by the greenhouse theory, and available models do not simulate sun's electric and magnetic influence on cloud dynamics. This table summarizes the principal differences between the greenhouse hypothesis and the new Nikolov-Zeller data-driven climate concept. According to the greenhouse hypothesis, the overall thermal effect of Earth's atmosphere is about 33 degrees. The analysis of Nikolov and Zeller have shown that the overall thermal effect of Earth's atmosphere is about 90 degrees, or 2.7 times higher. According to the greenhouse hypothesis, the atmosphere warms Earth's surface by impeding the loss of radiant heat to space through absorption and re-emission of outgoing long-wave terrestrial radiation by trace gases. Nikolov and Zeller found that the atmosphere warms Earth's surface adiabatically through the force of air pressure, which enhances the energy received from the sun in a way analogous to compression heating. Remember that the Earth's surface is under a constant gas compression. The greenhouse hypothesis asserts that Earth's global temperature is sensitive to changes in atmospheric concentrations of trace greenhouse gases, thus human-induced carbon emissions can affect climate. Mikolov and Zeller found that Earth's global temperature is independent of atmospheric composition. Non-condensing trace gases do not have a measurable impact on climate due to their small partial pressure in the atmosphere. Thus, the sensitivity of the climate system to human-induced carbon emissions is essentially zero. According to the greenhouse hypothesis, CO2 is a control knob of Earth's climate on virtually all time scales, that is, from decades to millions of years. According to the Nikolov-Zeller concept, Earth's climate is controlled by different forces on different timescales. Changes of global cloud cover induced by the sun through Birkeland electric currents and magnetic modulation of the galactic cosmic ray flux are responsible for the observed Decadal to Centennial fluctuations of climate. Changes of total atmospheric mass and surface air pressure drive climate dynamics on timescales of thousands to millions of years. In conclusion, results from our analysis show that the bulk of planetary albedos is an emergent property or a byproduct of the internal kinetic energy of the climate system rather than an independent driver of climate. We call this a baseline albedo. There is no meaningful relationship across planetary bodies between the average absorbed solar radiation, which is a function of total albedo, and the global surface absolute temperature. However, there is a well-defined mathematical relationship between albedo deviations from a baseline value and the resulting departure of the planet average global surface temperature from a long-term mean. Due to the presence of negative feedbacks in the climate system, only a small fraction of the cloud albedo is subject to modulation by external forcing, restricting global temperature variations on Earth to about plus minus 1 degree Kelvin on decadal to centennial timescales. This is what we've been experiencing as climate change for the past 160 years. Predicting future climates will require a deeper understanding of the cosmic forces controlling Earth's cloud albedo. However, the available data clearly suggest that albedo-induced global temperature fluctuations cannot cause a runaway climate change. Compared to the greenhouse hypothesis, the new NZ concept offers a much simpler and physically more robust explanation of climate system dynamics across various timescales. Specifically, this concept does not depend on putative mechanisms inferred from theory but never observed in reality, such as heat trapping by trace gases in an open convective atmosphere, which is physically impossible, or positive water vapor and lapse rate feedbacks that raise surface temperatures with no involvement of diabatic or adiabatic thermodynamic processes. The NZ concept, rooted in observations, also resolves fundamental theoretical inconsistencies in our understanding of the climate system, such as the 90-degree atmospheric thermal effect on Earth, which cannot be explained by an atmospheric absorption of outgoing infrared radiation as proposed by the greenhouse hypothesis. Finally, the NZ concept points towards new areas of research where future funding should focus, including processes controlling mantle degassing and loss of atmospheric mass to space, which determine long-term changes of surface atmospheric pressure and global temperature, as well as cloud albedo modulations by sun's electromagnetic forces that are responsible for short-term climatic variations on Earth. Thank you for watching. If you have questions or comments, please email us at nnikolov02@gmail.com. We're very interested in your feedback.